Okay, folks, we're going to come back to chapter 3, the composition of substances and solutions. The piece we really want to come back and focus on is this idea of ownership or agency, the self regulation of learning. And again, I think as you're going forward and getting ready for exam one, you can think about this in terms of how you can plan and set goals for how you want to study. And then think about the strategies that you want to use to check your performance, and then be able to reflect on that performance and make changes based on how you can improve. So, if we're thinking about designing and implementing methods of gathering information and data to answer questions, let's take a look at two. So, we have seawater contains roughly 28.0 grams of NaCl per liter. What is the molarity of sodium chloride in seawater? And then the density of surface seawater ranges from about 1020 to 1029 kilograms per meter cubed. So depending on the temperature and salinity, what is the range of density in grams per milliliter? So if we think about that first problem, we have 28.0 grams of NaCl, and we have 58.44 grams of sodium chloride um, as our molar mass. So that's adding the mass of sodium, the 22.99 grams per mole, to the mass of chloride, 35.45 grams per mole. And so once we do that, we have 1 mole of sodium chloride relative to 1 liter. And so that would give us then um, our moles per liter that we're looking for in terms of our unit. So that's 0.479 molar. And we want to remember that M stands for molar or moles per liter. So that's the unit that we're looking for. So we're going to multiply across the top, divide by what's on the bottom. Think about this other problem. Because we're dealing with a range, it means we actually have to do two calculations. So we have 1020 kilograms per meter cubed. And so we're going to convert our kilograms to grams. And then we're going to convert our meters cubed to liters. And then we're going to convert our liters to milliliters. When we multiply across the top and divide by what's on the bottom, that gives us 1.02 grams per milliliter. If we do a similar calculation for the other number that's in our range, that's 1029 kilograms per meter cubed. And so if we convert kilograms to grams, meters cubed to liter, liters to milliliters, that's 1.029 grams per milliliter. So we have 1.02 to 1.03 grams per milliliter. And so this is the range that we would report. I want to share out about Nicole Hernandez Hammer. So she has her master's, and it's from the Florida Center from Environmental Studies is where she did her research. But she's also a member of the Union of Concerned Scientists, and she's really interested in how climate change is affecting communities of color and low-income communities. And so she does a lot of outreach to the general public, thinking about the impact of climate change on those communities. If you recall, we talked about designing and implementing methods of gathering information and data to answer a question. And one of the things we're doing is learning how to interpret graphs. And so, for example, we can interpret this graph and ask some questions. So, for example, if we're thinking about the amount of salt in seawater, and then we're interested in the composition of that salt in seawater, we can do a mass percent calculation. So what is the percent by mass of chloride in seawater if there is 19.35 grams of chloride per 1 kilogram of seawater? And so you have 19.35 grams per 1 kilogram of seawater. And then if we do that conversion to kilograms and then multiply by 100, we have 1.935%, or roughly 2%. If we think about our learning outcomes for this chapter, we're thinking about mass percent as a conversion factor. We want to be able to convert between mass and number of particles. We want to calculate molecular and empirical formulas from experimental data. And then we want to use molar concentration to convert between the volume of solution and moles of solute. And then last but not least, we're going to use the dilution equation to relate volumes and concentrations of a solution. So let's think for a moment about our science practices. We want to think about asking questions and defining problems, as well as analyzing and interpreting data, and then constructing explanations or designing solutions, and engaging in argument from evidence. You're going to be able to do the finding of empirical formulas in your lab from this week, which is where you're thinking about copper and sulfur and this process of being able to find an empirical formula. In order to make sense of that, we want to think about how we calculate mass percent. So if we think about mass percent, we're thinking about the mass of copper in the total mass of copper sulfide. So remember, it's always a ratio of part to whole. And so we calculate the mass of copper in our numerator, and then calculate the mass of our sulfur in our denominator. And then if we do our calculations, we should have 127.1 grams per mole copper divided by 159.17 grams per mole copper sulfide. We multiply that by 100, that gets us 79.85%. It's important, if we're thinking about finding these empirical formulas, that in addition to being able to calculate our mass percent, that we can also use it as a conversion factor. And so if, say, for example, we were given 1.3 kilograms of copper sulfide, that we could convert that using our mass ratio to be able to figure out how much copper there was in our total sample. So 1.038 kilograms copper, or at least in terms of our reported value, 1.0 kilograms copper. So if we think about then using mass percent as a conversion factor, here's a quick summary, right, of the same calculation. So it shows you the setup as well as using it as a conversion factor. Let's think about finding the empirical formula. So if we have laboratory analysis of aspirin that was determined to have the following mass percent. So carbon was 60%, hydrogen was 4.48%, oxygen was 35.53%. And then we're going to use 4 steps. We're going to convert our percent to mass. We're going to convert our mass to moles. We're going to divide by the smallest amount of moles, and then we're going to multiply until whole. So we're going to assume that we have 100 grams. In order to solve this problem, we have to make that assumption. Then we can convert our percentages, because it's out of 100. We can convert our percentages to grams. If we have 60%, then that becomes 60 grams. If we have 4.48%, that becomes 4.48 grams hydrogen. If we have 35.53%, that becomes 35.53 grams of oxygen. The next step in our calculation is we can convert the 60 grams carbon to moles of carbon, and we can convert our 4.48 grams of hydrogen to moles of hydrogen, and our 35.55 grams of oxygen to moles of oxygen. When we do that conversion, one of the things we're going to see is, right, the 4.9958 moles of carbon divided by the smallest number of moles that we have, which in this case is the moles of oxygen. That's going to give us 2.24. We do the same thing to carbon. We have 4.444 moles of carbon divided by, again, the smallest number of moles, which is oxygen. It's going to give us 2.0. And 2.2218 moles of oxygen divided by itself will give us a ratio of 1. So we need these numbers, 2.24, 2, and 1, to be whole numbers. So right now it's not a problem for 1 and 2, but this 2.24, we have to multiply by a whole number. And whenever we multiply, in order to get a whole number, we have to multiply everything. So I went through and I tried 2 and I tried 3, but that didn't give me whole numbers. So I ended up with 4. So 4 times 2.24 gives me 9. When I multiply 2 times 4, that's 8. And 1 times 4 is 4. And so that gives me my overall formula of C9H8O4. So note here, I tried multiplying by 2 and 3, but they did not give me a whole number within 0.1. If we think about finding molecular formulas, we know the molecular formula is a multiple of the empirical formula, and the molecular formula can be determined from the empirical formula and the molar mass of the compound. So, empirical formula of acetic acid is CH2O, and its molar mass is 60.05. What is its molecular formula? Well, in order to do this, we have to find the molar mass of the given, which is 12.0 0.001 grams per mole carbon, plus 2 times 1.008 grams per mole hydrogen, plus 16.00 grams per mole, which equals a total of 30.026 grams per mole. We then need to make a ratio. So 60.05 grams per mole divided by 30.026 grams per mole. This is the molecular formula for the molar mass divided by the empirical formula molar mass. When we divide these two numbers, we get a ratio of roughly 2. So 2 times CH2O gives us C2H4O2. If we think about solutions and concentration vocabulary, so a solution is a homogeneous mixture, the solute is the minor component, and the solvent is the major component. Aqueous, right, is what we refer to when water is a solvent. It's often abbreviated AQ, and molarity is moles per liter. Dilution is making a solution of lower concentration by adding more solvent to a stock solution. So these are all key terms that we want to be familiar with when we're thinking about solutions and concentration vocabulary. Here we have two visualizations that we're going to think about in terms of how we make a dilution. So one way that we can make a dilution is where we add solid to a vessel. In this case, we're adding 1 mole of sodium chloride. So we're weighing out and adding that amount, in this case, 58.44 grams. And then we're going to add water. You're going to notice that in this vessel, there's a line. It's a volumetric flask. And so this line has a really specific meaning. It means that when you add water to the line, you're adding exactly 1 liter. And so this is a 1 molar sodium chloride solution. The other way to make a dilution is where we actually have a stock solution. So we're adding the amount of our stock solution. Notice there's a volume and there's a concentration. And then to that volume and concentration, we're adding water. We're diluting to a total volume, right? In this case of 3 liters. And that's going to give us a solution of 0.5 molar calcium chloride. So we can use our dilution equation of M1 V1 equals M2 V2, or C1 V1 plus C2 V2 to be able to figure out what the final concentration is. So if we think about our science practices and arguing from evidence, we can think about what is a claim, what is evidence, and what is reasoning. So we want to be able to argue from evidence about how we would prepare a 200 milliliter solution of 0.5 molar from a 1 molar solution of any one of these chemicals. So I chose HNO3. We have a volume and concentration, and a concentration, and then we're looking for the volume. So in this case, 1 molar is our most concentrated solution. We're multiplying that by a volume. And then we have our desired concentration and our desired volume. And when we multiply these two together and divide by our known concentration M1, that gives us a V1 of 100 milliliters. Notice that you could convert this to liters, in which case you would have liters here, right? And that would give you a final answer as well. Either one is acceptable. So to provide a claim evidence reasoning statement, in order to prepare 200 milliliters of a 0.5 molar solution, you would dilute 100 milliliters of 1 molar HNO3 with 100 milliliters of water. The 1 molar solution is more concentrated, so it is your M1. The givens are V2 and M2. This is a dilution problem, so we use the dilution equation to be able to solve it. All right. Science student success is right after class on Mondays and Wednesdays. It's a great opportunity to practice solving problems. Don't forget about coming to Chem 110 discussion. It's probably one of the best spaces to work on solving problems or answering questions. And then don't forget, you want to think about how you can organize your goals and think about your thinking and reflect on your learning this week when it comes to chemistry. So thinking about short-term targets to help you achieve progress. Think about, right, do you really get an idea? Could you explain it to a friend? Do you need more information or knowledge, or do you need more practice? And then to reflect on your learning, what made sense, what might need refining or reframing, what are you curious about? What are your next steps? All right, we'll talk about stoichiometry next. Have a great one.